Now we'll practice balancing redox reactions that are either in acidic or basic solution. In both these cases, we see that we're in acidic solution because we have H plus present. Steps are essentially the same as before with the simple reactions, except now we have a few additional steps. We start by determining the oxidation numbers that are changing. In the first problem, we're going to look at chlorine and chlorate and chlorine and chloride, as well as zinc and zinc. Now we're going to figure out the chlorate down here. We see 1 times the oxidation number of chlorine plus 3 times the oxidation number of oxygen has to equal the net charge. And the net charge here is -1 because this is an ion. And we've determined the oxidation number of chlorine in this ion is +5. This is the way we've done it. We have 1 times the oxidation number of chlorine plus 3 times the oxidation number of oxygen has to equal -1. That's our net charge. Chlorine plus 3 times -2 equals 1. We step through and we see chlorine must have an oxidation number of +5. On the product side, chlorine has an oxidation number of -1. It's a monatomic ion. Its oxidation number equals its charge. Zinc as an element is going to be equal to 0, and this monatomic ion of zinc is going to be +2. We're assuming that we have our steps handy, and we can follow along. You'll see that the next step is to balance those elements that are changing oxidation number, and they're already balanced because 1 chlorine, 1 zinc, 1 zinc. Next, we worry about electrons. We have chlorine going from +5 down to -1. So 5 down to 0 is going to be 5 units. 0 to 1 is an additional unit. There's 6 units of change, and therefore this process involves 6 electrons. 5 to 0 is 5. 0 to -1 is 1 additional. Now for zinc, it's being oxidized. It's going from 0 to +2, so it's losing 2 electrons. Now we want to balance the electrons lost to electrons gained. Lowest common multiple of 2 and 6 is 6, so we want 6 total electrons, which means the coefficients associated with chlorine remain unchanged, but we need to triple the amount of zinc. So we need to change these coefficients from 1 to 3. Thus far, this process is exactly the same as it's been for balancing simple reactions. Now we need to go further. The next step is to balance the charge either by adding H plus if you're in acidic solution or hydroxide if we're in basic solution. We can see that we're in the acidic solution, so we're going to balance a charge by adding H plus ions. So we're taking a look at the charge thus far. So we have 1 chlorate and 3 zincs. On the reactant side, we have a net charge of -1, 1 chloride, 3 zinc 2 plus, so we have a net charge of +5 on the product side. We need to balance the charge. What we have to balance charges is H plus ion. So in order to balance a charge, we're going to have to add 6 H plus ions, and that brings us to +5 on the reactant side, which matches our +5 on the product side. The last step is to balance the oxygen atoms by adding water. So if we look at our oxygens, we see we have 3 oxygens on the reactant side. We need 3 oxygens on the product side. The only place that the oxygens appear is in water, so we're going to need 3 waters as well. if we've done everything perfectly to this point, our hydrogens are also going to balance. So let's check our hydrogens. 6 hydrogens on this side, and 3 times 2, 6 hydrogens on the product side. We're done. So now let's balance the second equation. Looking at the elements that are changing oxidation number, we're going to have chromium and vanadium. For the oxidation number of chromium in this ion, we have 2 chromiums and 7 oxygens. The sum of the oxidation numbers has to equal the net charge, which we see is -2. All right, if we step through our algebra here, we see that chromium has to have an oxidation number of +6. This vanadium ion has an oxidation number of +3, and let's work out vanadium in this ion. All right, we're going to find the oxidation number of vanadium. There's 1 vanadium atom. We add 2 times the oxidation number of oxygen, which is going to be -2. The sum of these oxidation numbers has to equal the net charge, which we see is +1. And we walk through our algebra to find the charge on vanadium is +5. Our last element, chromium, here it's a monatomic ion. It has an oxidation number of +3. We connect up those things that are changing oxidation number. Okay, now we want to pay attention to our subscript here. Before we worry about electrons, we have to make sure we balance the atoms that are changing oxidation number. So we're going to need 2 chromium 2+ ions in our products. Now we can worry about our electrons. Vanadium is going from +3 to +5. It's being oxidized by 2 units, and therefore there are 2 electrons that are being lost. With chromium, we have to be careful because there's 2 chromium atoms. Each are going from +6 to +3. There's a net gain of 6 electrons. Each chromium is being reduced by 3 units, but we have 2 chromium atoms. 2 chromium atoms, each changing by 3 units, means 6 electrons as written. Now we need to balance the electrons lost to electrons gained. 2 and 6, the lowest common multiple is 6, so we need to triple the coefficients associated with vanadium. Those associated with chromium remain the same. Now we balance the charge. We're going to balance the charge by adding H+ ions because that's what we have present in solution. So let's look at our charge as the equation exists. All right, we have 1 dichromate. Its charge is -2, but we have 3 vanadium 3 ions. So we're going to have a net charge of +7. On the product side, we have 3 +1 ions plus 2 plus 3 ions. So you have 3 plus 6, a +9 on the product side. To balance a charge, we need an additional 2 plus units on the reactant side, which means we need 2 H+ ions. Now the final step is to balance the oxygens. So we see we have a total of 7 oxygens on the reactant side. Thus far we have 6 oxygens on the product side. So we need 1 additional oxygen in the form of water. So if we've done everything right, our hydrogens are also going to balance. So let's see, we have 2 hydrogens, we're done.